Okay, so we're moving straight into Chapter 3, which is all about Kmaps and circuit simplification. When we left off, we had actually just reduced one equation. I said that there were two basic rules. It's not showing up, is it? Better. Rules for Kmap simplification. 1, put in ones for all desired minterms. Zeros everywhere else. Okay, so for every minterm in your desired equation, or in your given equation, you put a 1 for that minterm in the particular cell. Step 2, circle rectangles or squares of ones until no 1 cells remain uncircled. And then you have your reduced equation. Well, except for this one little piece. Today, that's where we're going. Okay. The magic to get from a bunch of circles to a reduced equation. So let's go in with a simple Kmap here. Here we go. We'll use a 4x4 grid. If it's a 4x4 grid, how many variables are in this equation? How do you go from number of rows and columns?
It's going to be 4 variables.
How did you come up with 4?
2 on the that side, 2 on top.
Vertical and horizontal?
Yeah.
Yes, yes. So if you have 4 cells, that means you need 2 bits to address each of those cells, and you do it in gray code 00, 01, 11, and 10. And also on the vertical here, we have 00, 01, 11, 10. So that means we have a total of 4 bits. That's 4 variables. X, Y, Z. I'll call them W, X, Y, and Z for now. And let's throw some numbers in here. The interesting minterm. So this has quite a few minterms. Each minterm, remember, is going to consist of all 4 literals. Literal is just the letter. So this cell right here corresponds to W bar, X bar, Y bar, Z bar. Or what's the next one? W bar, X bar, Y, Z bar. That's this cell here. So we have a total of 8, 9, 10 terms. I might be able to finish writing the equation by the end of class, but I'm going to show you that it is actually quite simple to reduce this. So what I said was you're going to be circling squares or rectangles. The only trick is the squares and rectangles, so this is sort of addendum number I. Squares / rectangles must be a power of 2. So, what is the biggest rectangle of ones, contiguous ones, on this particular thing? Go ahead. You're pointing at something. What do you see? If you can't find a single square, maybe this isn't the course for you. Go for it. The first one, this one? That is a small square. It's just one. It's 1 by 1. What's the biggest? The one in the middle. Talk to me about that. How many rows tall is it? How many columns wide is it? Columns are these things. Rows are those things. 2 columns wide. How many rows tall is it? 2. 3. I heard 2 different answers there. Somebody shouted out 3. That's a pretty big rectangle. 2 by 3. But it does not meet the requirements of addendum I. Must be a power of 2. What power of 2 equals 6? Or 9? Don't know where 9 came from. No, that's not a thing. Powers of 2. 1, 2, 4, 8, 16. So, your answer was correct. You said it's 4, or it's 2 by 2. 2 by 2. Here I've got a 2 by 2 grid. That is a valid, what we call implicant. Now that also means, where are there other groups of 4 here? You pointed first, so you got to tell me. Describe it. The bottom 2 rows in the middle. So this guy right here. Well, now that brings up an interesting point. Can we circle things more than once? The answer is yes. You're allowed to circle cells multiple times. But there's a giant but on this. Multiple times. If, and this is the huge part, if at least one new cell is circled. So in this case, we've got 2 new cells that are circled. So it's perfectly okay. Because the rule of simplification with Kmaps is we always want to circle the largest square we can. What else do we have? Yes? The entire bottom row. Absolutely. There it is. That is a rectangle. It is 1 by 4, which means the total number of cells is 4. That's a power of 2. However, you just did something interesting here. So far, I've circled this middle group, this bottom group, and the bottom row. What do you notice now about this grouping here? Yeah, it actually doesn't add anything anymore. So if I were to not circle this bottom group of 4, this red group would still cover this cell and this cell, and the middle group would cover this cell and this cell. So this, what's called implicant, is irrelevant. Okay. Now, we'll get to that. We'll get to a way to avoid accidentally circling implicants that are irrelevant. But let's look at one more thing. We still have a few more things to circle. Technically, circling this 1 is not that great. There are better ways to circle that. But how can we circle that in a group if it's off by its lonesome? It's not touching anything. Look, there's nothing here. There's nothing here. Yes? We can wrap it around. So remember, this is a device that wraps around. So actually, this cell is next to this cell. So could we maybe circle it like this? That's a group of 2. Is there a better way? Could we go even further than this? If it wraps around this way, yeah.
Usually the same thing would be boss around, but instead of circling,
yeah, it actually will wrap around this way too, because it becomes a torus. Who did I make fun of? Torus? You had torus, correct? Somebody over here had donut. Yes, it's a torus. So actually, the way we would circle this is not to just circle those 2 rows, but because that cell is right next to that cell, it wraps around, we actually have a group of 4. So it's important to remember when simplifying that those 4 corners are actually right next to each other. You can make a group of 4 out of those. All right. So that covers a few things. Now, anything that you circle here is what we call an implicant. There are some implicants that are better than others. We have 3 basic categories. One is just an implicant. Second is what we call a prime implicant. And the last and most important is called an essential prime implicant. So they get better and better as they go along. Okay. An implicant, let's actually just go back here. An implicant is any cell that is allowed to be circled. So this right here, if I circled this cell, that's an implicant because everything that I've circled contains a 1. If I put a circle there, that's not an implicant because that's a 0. Okay? So an implicant isn't all that useful in reducing things because it could just be a single 1. And by 1, I mean a single cell that has 1. A prime implicant is the largest implicant you can make that covers a particular cell. So while this red box here is an implicant, this green box is a prime implicant. If we're reducing things, we should only ever be circling prime implicants. Okay, so a prime implicant is the largest, I can't say the word now, implicant, the largest implicant that can be circled. An essential prime implicant. Oh, by the way, this cell here, this is also a prime implicant because it is the largest group of 4 that you can circle. Okay, it is a prime implicant. Essential prime implicants, though, those are the holy grail. We want those. An essential prime implicant must be an implicant. It must also be a prime implicant, so the biggest it can be. But it has at least 1 cell that is not covered by any other prime implicant. So there, in this diagram here, there are 2 essential prime implicants. Circles that contain a cell that is not covered by any of the other prime implicants. Let me just redraw it here so you can see. Let me go like this. We've got the board here. My cells are here, 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 and here. If I circle all of the prime implicants, right, prime implicants cannot be made any larger. So this group of 4 cannot be made any larger. This group of 4 cannot be made any larger. This group of 4 cannot be made any larger. This group of 4 cannot be made any larger. So the question.
Just to be clear, it has to be groups of 4.
No, it could be groups of 2, it could be groups of 1, it could be groups of 8, it could be groups of 16. You cannot have an implicant that is not a power of 2. So that's the rule. You cannot do it because 6 is not a power of 2. It has to be a square or a rectangle that also contains a number of cells equal to a power of 2. So no one should ever circle a group of 6 or a rectangle that is only 3. Okay, it has to be 1, 2, 4, 8, or 16. Now, if you look at what I've circled here, you're trying to find prime implicants that have at least 1 cell that isn't covered by any other prime implicant. So this cell right here has 2 prime implicants covering it. It's circled by the one below it and the one above it. So what prime implicants aren't? What cells are only covered by 1 prime implicant? So tell me what the cell is. First cell, top left corner. This cell, okay, is only covered by the prime implicant that covers the corners. This cell in the top right corner also, but that's the same thing. So that 4 corners is what we call an essential prime implicant. And when we're reducing, we always want to circle those first. Are there any other groups or any other prime implicants? Yeah, the 2 in the top middle here. Okay, those are only covered by the implicant in the center. So both of these are essential prime. Are there any other cells that are only covered by 1? No, there are not. Okay, so things that I know, the 4 corners, that's an essential prime implicant. And the one in the middle is an essential prime implicant. If I circle all of those, okay, are all of my 1s circled? No. What 1s aren't circled? Yeah, the 2 in the bottom middle. So even though we have found all the essential prime implicants, oftentimes we're going to have to circle 1 or more prime implicants, even though strictly we don't have to. So the question is, which prime implicant do we circle? There are 2 possibilities. There's the red rectangle, and there is the blue square. Which one is correct? Is an excellent answer, surprisingly. Yes, either. Okay, they both do the job. Now here's the weird thing. If you circle the square and you circle the rectangle, your answers are going to look different. Your math or your algebra will be a different equation, but it will perform the same function. It's 2 ways of getting to the same solution. Okay, so for our purposes, let's circle the bottom row. So our rules for doing this is find all prime implicants. Circle the essential prime implicants. What we did here, by the way, circling all of this, we circled all of the prime implicants first. We identified what they were. Then over here, I circled only the essential prime implicants. And then I added prime implicants until everything was covered. And I did it in a greedy fashion. I try to cover as many cells or as many min terms as I can with a single prime implicant. Okay. The last step, if you do it poorly, if you do your choosing poorly, the last step is minimize overlap. Okay, so if you have a bunch of things overlapping, as this cell here and here do, you want to minimize that overlap. So you want to remove them if needed. Now, step 3 is still magic. All we've done is circle 1s. All right, it's an art lesson so far. When we are dealing with a 2x4 Kmap, we have a couple of options in terms of cells that we can circle. We can circle 1 cell, we can circle 2 cells, we can circle 4 cells, or we can circle 8 cells. Those are the only sizes available to us. Now, if we circle all 8 cells, that means that no matter what we put in for X and Y and Z, no matter what we put in, we get out 1. It's always going to be 1. Doesn't matter if X is 0 or Y is 0. It doesn't matter X is 1 or X is 0 or X is 1. Y is 0, Y is 1, Z is 0, Z is 1. Doesn't matter. We're always going to get 1. So if it doesn't matter if X is 0 or X is 1, X isn't going to be part of your final solution because it's irrelevant. Okay? If I give you an ultimatum that says you can only play outside if it's sunny, but the only information I give you is it's 73 degrees, does that information have any bearing on whether or not you can go play outside? No. Same thing with X. It doesn't matter. So what we say is if all 8 cells are circled, the answer is just true or 1. Now, if you circle 4 cells, your term, so this is going to result in a single term, and that single term is going to have 1 literal. So we have 3 literals to choose from, X, Y, and Z. But the term that corresponds to that red circle is going to be 1 literal wide. It will be either X or Y or Z. If we have 2 cells circled, that's going to have 2 literals. And finally, if we have 1 cell, all 3 literals will be involved. For a 4 by 4 cell Kmap, we're similar. We have 1, 2, 4, 8, or 16. 16 possible cells could be circled. And it follows very similarly. If we circle all 16 cells in a 16-cell Kmap, the answer is true. If we circle half of the cells, that's going to be 1 literal. If we circle 4, that's going to be 2 literals. If we circle 2, that's 3 literals. If we circle 1, that's going to be all 4 literals. Okay. So with that knowledge in mind, let's do a simple Kmap here. And we're going to actually finally turn this into an equation. So let's throw some 1s into this Kmap, 0s everywhere else. So now we need to identify all of the prime implicants. Whenever we search for prime implicants, we always start by looking for the largest possible contiguous block of 1s. So this is a 2 by 4 Kmap, so we look for a block of 8 1s. Any 8 1 blocks? No. So then we go down by a power of 2. Are there any groups of 4? No. Then we look for 2. We are never going to go down to 1 block, to the next lower until we've exhausted all of the possible options. So are there any groups of 2? Okay. Someone I haven't heard from, describe one of them to me. Yeah, bottom left 2 corners. That's 1 prime implicant. We don't know if it's essential yet because we haven't analyzed the whole thing. Another prime implicant. Bottom left corner to bottom right corner. You seem very pleased with yourself that you saw that one. That's true, though. That's definitely a prime implicant. Another. Yes? The 2 in the middle on the top. Yes. Any other prime implicants? Vertical in the second column. This is a prime implicant. It's not essential, okay? It's definitely not essential because both of those are covered by at least one other implicant. But it is a prime implicant. We have to circle it to know what's essential. So now looking at this, what are the essential prime implicants? First off, somebody raise your hand. How many do you think there are? How many essential prime implicants do you think there are? 3. Okay. Well, you're wrong, I think. So you tell me which 3 there are, and we'll talk about why they are or are not. Bottom 2 corners. And the 2 in the middle on the top? Well, you said 3. You decided to change your mind. Which one did you think it was?
No, I was going to say the left two.
Yeah, the left bottom two. It's covered by the vertical one, and that takes care of this cell. And then the one that goes off to the side is also one. So yeah, you're right. There are two. So as we circle these, those are our essential prime implicants. 1, 1, 1, 1, 1. Okay. So what cells are left to be covered? Second column, bottom row. So which one do we choose? Because there are two prime implicants that cover it. Which one is right? Both of them are right. I'm going to grab this one. I've decided this is the one I want to do. So now it's time to turn this into an equation. Now, based on what I told you last slide, since all of these are two-cell prime implicants, each of them is going to have two literals, two letters. Here's how you figure out which two letters and what they look like. First, you got to make sure that you have labeled your Kmap all the way along. Okay, very important to do that first. Then what you want to do is you want to find similarities for the things inside of your prime implicants. If inside of a prime implicant a letter stays the same value for all of the cells, okay, it is included. For example, look at this bottom left and bottom right corner. It's in the row where X is labeled 1. So both of these cells have X equal to 1. What about their columns? What's true about both of these columns, the far left and the far right column?
Z equals 0. Z is labeled 0.
Yeah, Z is labeled 0. Y is 0 and it's 1. Does everybody see how Y in the left column is 0 and in the farthest right column, Y is 1? So if something changes, it is not part of your solution. So this term is going to be written as X, Z bar. If you see a 0 in common to all the cells, you put an overbar over something. Let's look at the vertical, this guy here. Does X change between the top row and the bottom row? It does, yes. So X is not part of the solution, or the term, I should say, the term that we're looking for. What is Y in both of these cells? It's 0. It's actually pretty easy to see because we're just in that column. We can just read off that Y is equal to 0 and Z is equal to 1 because in that column, Y is always 0 and Z is always 1. So our term is Y bar Z. I would like you to try and tell me what this term is. The middle top two. What do you think?
X not Z.
X not Z, because X is 0 in this whole row. So since both of these cells are in that row, we know that it's X not. And Z, because in this column and this column, Z is 1. And that's it. So our function of X, Y, and Z is equal to X Z bar, Y bar Z, or X bar Z. This is a guaranteed, completely reduced sum of products form. Move it over a little bit. Sum of products form. It is not necessarily the most optimal to implement, though. Yes? The Y bar Z? Yes. So what I did was I looked for commonalities. these two cells have some things in common. Between the top cell and the bottom cell, x changes. In the top cell, x is 0. In the bottom cell, x is 1. So x is not part of the solution. Now in that column, this first digit represents y every time, and that represents z every time. So this is yz, 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 yz. So all I did was I looked and I said in that column, y is 0 and z is 1. So if it's 0, you put a bar over the y. That's correct. If x, so just like the first term, y changes between this column and that column. Here it's a 0, here it's a 1. So y is not part of that term because it changes. It's the same thing as I told you the temperature, but what I was really asking about was, is it sunny? You cannot determine that information. It doesn't matter what the temperature is. Okay? It doesn't matter what y is. If x is 1 and z is 0, you will get a true, whether y is 0 or 1. Now, algebraically, what we did here was we had two terms. We had x, y bar, z bar, or x, y, z bar. Those two terms algebraically combined to form the term x, z bar. You can follow it through. You can look at this min term and this min term, and you will see that they do in fact come out to those two terms, those two min terms. If you algebraically factor out x, z bar from both of those terms, you're left with y bar or y. Y bar or y is just equal to 1 based on our rules of Boolean algebra. And then 1 ANDed with anything is itself. So we end up with x, z bar. So it's still doing the same process. We could have done this using Boolean algebra. But it's a heck of a lot easier to see visually. It's just how humans work. We're really good at pattern matching. All right, could somebody fill me in on what I gave as a function, please? A, B, C, D. Sum of min terms.
0, 3, 5, 7, 10,
10 what?
14,
14 and 15. So that's 0, 3, 5, 7, 10, 14, 15. That's what I gave everybody. You can't see it yet. Let's do full screen preview. Boom. Okay, we're back in business. So filling this in, first thing to remember is that we are doing things in gray code. So we don't just count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It gets a little bit more confusing than that. It has to be that way, though, in order for that simplification process to work. So very briefly, let me write down what the cell numbers are. 3, 2. So it's 0, 1, 3, 2, 4, 5, 7, 6. I'm going to skip the third row entirely and say 8, 9, 11, 10, and finally go back to the third row for 12, 13, 15, 14. So filling this out now, 0, 3, 5, 7, 10, 14, 15. Let me just make sure that that is kind of what I wanted to do. Flip that around like that. Looks pretty good. So those are my cells. So in yellow, I'm briefly going to try and find all of the prime implicants. Yellow because it's kind of easy to ignore. So again, I start by looking for 16s. Are there any groups of 16 ones? No, of course not. Because we would need all of the cells to be 1. Any groups of 8? No. Any groups of 4? No. So we're down to groups of 2. So I can just start circling groups of 2. I'm not looking for essential prime implicants right now. I'm just looking for anything that is a group of 2. What about this cell? Can this cell be combined in a group of 2? It can. Tell me what min term numbers to circle.
0.
0 and 10 is not correct. Okay? And sort of the point. You cannot circle diagonally. Those are not actually connected. It would not be legal, for example, to circle 5 and 15 because those aren't next to each other. They're kitty corner from each other. So you cannot circle. You cannot circle those two corners. Even though, yes, technically it does wrap around, it doesn't wrap around so that they're next to each other. So this cell, circled just like that, just by 1. Now, some people it surprises that that single cell is an essential prime implicant. Okay? It doesn't have to be the biggest on the board. It just has to be the biggest that could possibly circle that cell. The only way to circle cell 0 is to circle just cell 0 by itself. So that makes it an implicant. It makes it a prime implicant because it's the biggest one you can make, and it's essential because no other cells or no other implicants circle that cell. So looking for essential prime implicants, that is definitely an essential prime implicant. This is an essential prime implicant because of cell 3. This is an essential prime implicant because of cell 5. This is an essential prime implicant because of what cell? Because of cell 10. So we've got 1, 2, 3, 4 essential prime implicants. Are we done? No, because we have to circle what cell? 15. So which one do we choose? Well, we could circle either 7 and 15, or we could circle 15 and 14. I've colored them red and black, so we'll do both. All right, so as we go through this, now we need to find commonalities between the cells. So our first implicant is this implicant here. So what values are common to that one cell? It's all of them, and they're all 0 in this case. So this implicant is A, B, C, D, with each term inverted. A naught and B naught and C naught and D naught. Yes? A has my face over it. Well, thank goodness for movie magic. Okay. So that's our first term. Next, let's go after this horizontal prime implicant. So let's do the row first, because the row is the easy part. We just look. Since both of these cells are in the same row, we can just read off the row. A bar B. It's a given. If you're entirely within a row, you just look at the row value and put it down. Now it spans 2 columns. Now between 2 columns, one variable or one literal is going to change and one's going to stay the same. So the one that stays the same is this one. It stays 1. So it's going to be D. It's not C because C is first. C changes from a 0 to a 1, so C is not involved. So that's A bar B D. Let's look at this implicant. So here, the same trick that I just did with the row, I can do with the column. I'll leave a space for the AB part, but the column, since these two are both in column 1, 1, that means I'll have CD. What will the rows tell us? It's in row 0, 0 and 0, 1. So what's the same between those 2 rows? A is the same, and what's the value of A? A is 0. If A is 0, we say A bar. All right, let's also now look at this one, 10 and 14. Somebody volunteer the entire term for me. Cell 14 and 10. Yes? B, C, D. I think you have the right literals, but maybe not the right status of those literals. well, actually, hold on a second. No, I don't think you have the right literals. No, somebody else help him out. In the back. ACD, I think we're getting closer. Say it again. D bar or D naught. It has to be D naught. So it's A because it's 1 in both cases. A, B. So B changes. So B is definitely not a literal. A stays the same between those two rows, so it's A. And it's 1, so it's A, not A bar. Then we look at this column, and it's CD. So it's a C positive, D negative, so the D bar. Okay. Now, then we have a choice. We can either circle the red one, and the red one would be B positive, C positive, D positive. That's red. Or we could circle the horizontal, and that would be A, B, C. So very different terms, including totally different literals. It is a mistake. It is wrong to include both. Not both. Only one. Okay. Now, 5 minutes is a little tight. This does give us a sum of products representation. I'm going to jump right in. We'll have a preview of coming attractions. If I asked you to give me a product of some implementation, it's actually not as easy with Kmaps. Kmaps naturally give us sum of product information. Let's give you a quick Kmap here. Now, I have trained you thus far today, and yes, and on Monday, to circle the ones. So there are my ones. What if I asked you to apply the same rules and circle zeros? If I asked you to circle zeros, you might say, okay, there's a group of 4, there's a group of 4, there's a group of 4, and ooh, that's a good one. There's a group of 4. Almost all of those are essential. I think actually all of them are essential. Each and every one of those is an essential prime implicant, and I've circled all of them. Now, if you apply the same rules, A, B, C, D, to each of these terms, what do we end up with? Well, looking at this, F of A, B, C, D, I'm circling the zeros. So what I'm really finding is what F isn't. That's going to be A, B for the horizontal term, C, D for the vertical term, B, D naught for the outer two edges. And is that it, actually? Yes, actually, there was one that was not essential. This one right here. That was just a prime implicant, so I'm not going to solve that one. So there I am with those 3 things. Now, that tells me what F isn't. Now, one of the things I always want you to think of when you see something with an overbar is of my favorite law. What's my favorite law? Yes, De Morgan's law. So if this is F bar, it's F bar, it's what F isn't, I could invert both sides, and F double bar is just F, right? So I could say that F by itself is equal to this. Nothing scary there. Now, we would have to apply De Morgan's law to simplify this. Let's do that quickly. applying De Morgan's law. Come on. Uh-oh. Let's apply De Morgan's law to the whole thing. Applying De Morgan's law, what's the mnemonic for De Morgan's law? Split the line. Maybe we need to say this again as a group. Can we all say it together? Split the line, change the sign. 1, 2, 3. Split the line, change the sign. Yes, Professor Vile is so mean. He makes us talk in class. Split the line. We have 3 terms that are ORed together. So I'm going to have A, B, and then change the sign. So the ORs turn to ANDs. This is CD. This is B, D not. Unfortunately, we're still not done. We need to apply De Morgan's law to each of these terms. So this term is going to become A bar or B bar. This term is going to become C bar or D bar. This term is going to become B bar or D double bar, or written another way, B bar or D. And I just made one tiny error there. That should be ANDed. Now, F of A, B, C, D, this is a product of sum representation. So there are 2 ways of skinning this cat, of solving. If you want to find sum of products, circle the ones, and it gives it to you in sum of products form. If you want to find product of sums, circle the zeros, and then apply De Morgan's law. Email will be coming out in homework. It is out of the book. It is out of the 5th edition of the book. So if you don't have the 5th edition, get with a friend real quick and figure out which problems it is. So you have that email within a little bit. I will see if I can recover the first half of the lecture video and post it on YouTube.